again, in the name of the Almighty, the Compassionate, the Merciful. We look here to the, in this lesson we are going to focus on some properties of the definite integral. These properties in fact concern functions which are only integrable. In other words, they're not meant to be for functions which are continuous. It's immaterial whether the function is continuous or not, but they are meant to be mainly for functions which are integrable. If f is integrable, then we may be able to draw some conclusions about it. And in this lesson we are going to speak about the properties of integrable functions, and then some useful theorems on parity. By parity we mean either the function is even or odd, etc. And we're going to speak about the integral mean value theorem. And the integral mean value theorem here, it looks very much similar to the one that we have already studied, remember, in our lesson 13, when we considered the application of the derivative. That was the first lesson in the application of derivative, and there was a theorem called the mean value theorem, in which one can relate the value of a function between 2 points by the derivative at a point in between an open interval AB, in which the function is differentiable. Suppose we start by the first few properties. These properties are in fact very trivial, and you can get them, you can directly notice them, and of course you can prove them. There is nothing without proof, but it's simple. You can you rely on your instinct. There is no point of proving everything, as we said before. For a student, if he feels that this is true, then unless he is asked to prove something, then he may directly go for his instinct and give the answer direct away. For example, this function here is constant. If the function is constant, what is the integral of f(x) dx between 2 points AB? Directly you notice that since the function is constant, then of course you may get f of x, you may substitute f of x for c. This is the value of the function, which is constant, is equal to c. So you may substitute f of x equal to c, and you directly obtain c times the integral between a and b, the integral between a and b of 1 dx, and the integral of 1 is equal to x, and if you substitute x between a and b, you get directly b minus a. In other words, the area is equal to c times b minus a. But you need not do this. You can direct away obtain the same result by noticing that since the area is equal to the area, the area under this curve here is equal to area of this rectangle, the area of the rectangle is equal to the height times the base, so the base is equal to b minus a, and the height is equal to c. So directly you can reach this result, which is equal to c times b minus a. Now, if f and j are both two integrable functions on the closed interval AB, remember that in other words, we mean that f and j are both Riemann integrable over the closed interval AB. The first property here, we can have, for example, the integral from a to a. And this is again direct, it's equal to 0. Why is equal to 0? Because here you have a zero norm of partition, if we want to make it a little bit rigorous. But you can also say that the area is between a point A and a point A. So actually there is no base, since the area is equal to the base times the height, and the base is 0 in length. So it means directly that the area must be 0. But you may, of course, do it otherwise by taking the limit of your Riemann sum, and then your norm of partition is equal to 0, and therefore your integral must tend to 0, etc. These kind of things, of course, you may follow this routine of proofs, but yet your instinct again tells you directly that the integral must be 0. A second property, for example, the area, the integral from a to b is equal to the area minus the integral from b to a. And again, for example, the integral from 0 to 1. If you know the integral from 1 to 0, should you do the integral again? No. You rely on the integral from 1 to 0, and then you insert a negative sign. You change the sign of the integral. And the reason why this is that because your base, instead of being xj minus 1, it's xj minus 1 minus xj. So again here your dx must change in sign, because instead of summing up in the positive direction, you sum up in the negative direction, and when you go in the negative direction, your x is negative, and therefore you end up with this property here. So for example, suppose we wish to evaluate the integral from 1 to 0 to square root of x dx. And you know already the integral from 0 to 1 of square root of x dx. And we actually, we have calculated this in our previous lesson directly when we use the norm of the partition, the different norm of partition. Remember the different rule of subdivision, I would say instead. The different kind of partition. When we choose a partition which does not yield an equal subdivisions, we end up to the calculation of this integral, and you found it out is equal to 2 over 3 when it is from 0 to 1. So suppose we wish to calculate the same function, the integral of the same function, but from 1 to 0. So you rely on our previous property, which was just displayed here on the previous slide, and you say directly that since the integral from 0 to 1 is equal to 2 over 3, therefore your integral from 1 to 0 is equal to the negative of your integral, in other words, the same value but difference in sign. So instead of positive, it's negative, and therefore your integral is equal to minus 2 over 3. So you see, these properties allow you, knowing some kind of integral, some sort or some values for integrals, you may use them to evaluate some other form of integrals. This is another property which is always true. Sometimes you have a function which is composed of many pieces, of many functions, and you wish to integrate the whole function over an interval from a to b. How would you do this? Of course, you divide it into several pieces. For example, you have sine plus cosine dx from a to b. So you say that this is the integral of the sine plus the integral of the cosine. And in fact, here it is. Suppose, for example, you have f of x minus g of x. So what you say is the area. Since the integral means area under the curve, so suppose this is the function f of x. The first one here, the upper one, and the lower one, it is g of x. So what you have in between is what? Is f of x minus g of x, the length, the height of the lamina. Each lamina, you have here some rectangular laminas which are all elevated here. They're all vertical laminas. They look like rectangles, and the area in between these two graphs, which is f of x minus g of x, represent the height between the two times delta x, and you just directly see that this area is equal to the area below what is below the first function minus the area what is below the second function, and you get what's in between. So in fact, if you wish to calculate an area comprised between two curves, what you do is that you calculate the area between under the first one minus the area under the second one. Or you may also do it this way. For example, in other words, we may do it on the contrary. In other words, we do it reversely. Instead of saying that the integral of f of x plus g of x is equal to the sum of these two integrals, we may say that the sum of these two integrals is equal to one integral, and you subtract these two values of f in order to calculate the area between the two functions, between the two curves of the functions. For example, evaluate, here is another example, the same, which display the same property. You have the integral from 0 to 1 of x plus x squared dx. In order to integrate here, of course, you are looking for antiderivative. But again, we don't speak about antiderivatives. In other words, we are not speaking about functions which have antiderivatives or functions which are continuous. This is not the case. The case we speak about functions which are integrable only. And this is why in this situation here, when you decompose this integral into the sum of two integrals, here we don't speak of calculating via the fundamental theorem. In other words, we don't look for an antiderivative of x is equal to half x squared, and then you substitute from 0 an x. No, we just say that here you have a region comprised between a straight line and the x-axis, and this region, since it is a triangle, then the area is directly equal to one half, whereas the second area here, according to the result which was already displayed previously, even in the lecture when we considered the results obtained by Archimedes, he obtained that the area, remember the area, he was able to calculate the area under the parabola x square of the parabola y is equal to x squared, and in using our symbols, he was able to produce this result, that the integral from 0 to 1 of x squared dx is equal to 1/3, and therefore here is not a matter of being continuous or not. All we just say that these properties adhere to them the integrable functions that are integrable. Only these functions that we mean here. Functions, if the functions are integrable, then the integral of f of x plus g of x is equal to integral of f of x plus the integral of g of x, and you add up, you sum these two integrals in order to obtain the integral of the original integral. Again, when you multiply a function by a constant, and if you know the area, because this definite integral in fact represent area under the graph of y is equal to f of x between a and b. So if you multiply a function by a constant, so it's logical that you can calculate the integral of the function and then you multiply it by c. For example, like here, for example, we have here a function which is given by two rules, is equal to 1 from 0 to 1, and minus 3 from 1 to 2. In fact, we should give it here a value x greater than or equal to 0 because we are considering Riemann integral over a closed regions. In other Riemann integrals are defined over closed intervals. So in fact, we should give it another value here, 0, but it doesn't matter. The idea is the same. The function f of x, the graph, here it is the graph of f. The graph of f is equal to 1 from 0 to 1, and is equal to minus 3 from 1 to 3. And suppose we wish to calculate the integral of 5 times f of x dx from 0 to 2. So what we do is that we calculate this area, and this area is equal to what? This area is equal to, here is positive and here is negative, here is equal to 1, and here is equal to minus 3, the height times 1. You get minus 3 plus 1, which is minus 2. And then if you wish to calculate the integral of 5 times this function, so all you have to do, instead of calculating again the integral, all you have to do is that you multiply this value here by 5 in order to get minus 10, which is the value of your integral of 5 times f of x dx. Again, here, suppose, for example, that I have a function which is integrable over a closed interval AB. Am I able to, for example, to subdivide the region AB, the interval AB, into, for example, two regions, AC from A to C and from C to B, and say, for example, that the integral from A to B is equal to the integral from A to C plus the integral from C to B? In fact, you can, and this is here. It's clear here. Why? Because the region, the area under the graph, under the curve y is equal to f of x from A to B, is equal to the sum of the areas of the two areas. The area under the same graph in the interval from A to C, and then plus the area under the same graph in the interval from C to B. So you can, in fact, decompose your interval into two regions in which you sum up the two integrals in order to get the whole integral over the whole interval from A to B. Yeah, for example, suppose you wish to express in one integral this I. Here it tells you evaluate the integral from minus 1 to 0 to f of x dx, minus from minus 1 to 2 to f of x dx. Would you do this alone and this again alone? You may do it, but you may also wish to calculate it as one integral. How? Here it is, you can revert actually the sign of this integral here, minus the integral from minus 1 to 2, and we have seen according to a previous property, is equal to plus the integral from minus 2 to minus 1. So if you revert the sign here, you get here what? You get the integral from minus 1 to 0 plus the integral from minus 2 to minus 1. So as if you're saying from minus 2 to minus 1 first, then to from minus 1 to 0. So in fact, you can combine both to obtain the same integral, but from minus 2 to 0. Now, if f is integrable on the closed interval from minus a to a, you can have some properties actually which facilitate the evaluation of integrals. For example, if f is odd, f is odd means that f of minus x is equal to minus f of x. Like, for example, you have sine x. For example, the curve y is equal to sine x. looks like this, from minus pi to pi. And it looks directly here that the integral, there is a difference between the integral and the area. The area has to be always positive because it's unit of surface. But the integral might be negative or positive. For example, here this is positive because you go along the x-axis, and y is positive, while here y is negative. So actually the area here is negative. I'm sorry, the integral is negative. So if you add up negative to positive, and of course you see that they are symmetrical with respect to the origin, and they both have the same area. So in fact your integral is 0 from minus pi to pi of your function sine x dx. So when you have an odd function, it may be easier to directly resort to a property of this sort. Whereas if f is even, in other words, symmetrical about the y-axis, like for example, it qualifies verifies the property that f of minus x is equal to f of x, like cosine, for example. The cosine functions is symmetric about the y-axis. So in fact, if you wish to integrate from minus a to a, you may not integrate over the whole interval from minus a to a. It's enough that you integrate from 0 to a and you multiply by 2. And the reason it's clear because since both areas are equal, so the sum of these two areas is equal to twice the sum of each one, and each one is equal to either from minus a to 0 or from 0 to a. So we multiply by twice from 0 to a, and this gives you the area, the overall area from minus a to a. For example, if you wish to integrate e to the minus mod x sine x from minus pi to pi, even without knowing the curve or the graph of this function here, how it looks like. Of course, you know it is here positive and here negative. But suppose you don't know it. Suppose you wish to check the parity. Here it tells you if you calculate f of minus x, or I mean if you find an expression for f of minus x, all you have to do is to substitute x for minus x for x. So you get here e to the minus mod x sine minus x, and you know that this doesn't change because the mod of minus x is mod x as well. So you get here e to the minus mod x, and sine minus x is equal to minus sine x. So in fact you get the same function but reverted in sine. So you know now that f of minus x is equal to minus f of x. So this function is odd, in other words symmetric about the origin. So in fact the integral from minus pi to pi for this function is 0. And there is no need to carry out conduct the integral, and you may be pleased by applying the property instead of checking the value of the integral after integrating the function, and which you may lose time, and this gives you directly an answer to your problem. For example, here your function is here. It looks even directly. Why? Because it's symmetric around the y-axis. Why is even from your graph? Or even no. Suppose you wish to check your parity, f of minus x, whether it's equal to f of x. For example, you can use minus x minus 3. And what you do here, you invert here x and you invert here x. You get here plus, and here if you invert x, you got something like this, minus 3. And you have to revert this. This is equivalent to what? You multiply by minus 1, so you revert your inequality. And you get what? You get f is equal to x plus 3 for x greater than 2, or and here should be equal to 2. Here you revert. If you revert it, you get directly the same expression here, which is x minus 3 from x greater than equal to 2 and less than equal to 3. So in fact, and it doesn't matter. It's not even immaterial because it is verified in the second inequality. So you find that if you revert the value of x here in the first rule, you obtain the last one. So in fact, it is verified that this function is even. But you need not to, because since they are straight lines, you wish to draw all these lines, and you directly notice that they are all that there is some kind of symmetry around the y-axis, and therefore the whole overall integral is equal to twice the integral from 0 till 3. Here it is twice the integral from 0 to 3, and therefore you get minus 1 for the overall integral. Now, suppose there is a symmetry, but not around the y-axis. A symmetry around a over 2, for example, a function which is integral from 0 to a, but around the axis y is equal to x is equal to a over 2. There is kind of symmetry. In other words, f of x is equal to f of a minus x. Yeah, like this. You have here. Here is your function. And you have here, this is your line of symmetry, and this is a over 2, and this is a, and this is 0. So this value here is equal to this value here. In other words, there is a symmetry around your line x is equal to a over 2. So you of course, you can apply the symmetry criteria here. In other words, from 0 to a, your integral from 0 to a is equal to twice the integral from 0 to a over 2 of the same function. Here is a very useful property, in fact. It tells you that without symmetry at all, the integral from 0 to a of f of x dx is equal to the integral from 0 to a to f of a minus x dx. In other words, when you add up here, suppose you wish to do the integral, you go this way. You might revert f of a, this is x, and this is a, and this is a minus x. So in fact, you can, instead of adding up in this direction, you can add up in this direction, and you end up with this property here. The integral from 0 to a is equal to integral from 0 to a, and you revert. All you have to do is to substitute a minus x for x. In fact, this can help you achieve a lot of results. For example, suppose you have an integral from 0 to pi by 2 of cosine x divided by sine x plus cosine x. In fact, to find an antiderivative of such function is difficult. But suppose I wish to use this property. So what I say is that your integral is the same as from 0 to pi by 2. All you have to do is that you substitute for x pi minus 2 minus x dx, and same thing here, sine pi by 2 minus x plus cosine pi by 2 minus x. And this gives you what? The integral from 0 to pi by 2 to this is equal to sine x, and this in fact becomes sine x plus cosine x dx. So in fact, instead of, when you see here, when you see these two integrals, it tells you that this integral is the same as this one. So since both are equal, so each one is equal to what? Is equal to half the sum, the integral of from 0 to pi by 2 to the sum of both, since this one is equal to this one. So if you sum both, you get what? You get sine x plus cosine x divided by sine x plus cosine x. But in fact, this is equal to what? Is equal to 1. And this equal to, so therefore you get what? As integral, half from 0 to pi by 2, in other words, is equal, your integral which you are looking for is equal to pi by 4. And this is how it goes, in fact. You use the theorem directly, and you end up with pi by 4. And the same applies here, for example. Suppose you wish to evaluate this integral, which is difficult, in fact. This integral here from 0 to pi by 4 ln cotan minus sec minus tan. So you can, of course, substitute for x pi by 4 minus pi over 4 minus x. And then you expand cotan pi by 4 by the difference of cotan of two angles. Same thing here. And you end up, when you perform a little bit of algebra, you end up with this integral here. But this integral here looks very much like the one we started with, is equal to what? Logarithm of 4 minus the logarithm of cotan x minus tan x dx. This one is the one that you are seeking to calculate. So here you have the integral of ln 4 minus the integral which is unknown, minus I. So since I is equal to this minus I, it means that, remember, like integration by parts, it means that twice I is equal to this integral. In other words, that I is equal to half this integral here from 0 to pi by 4 over ln of ln 4 dx. And since this is constant, you get directly half ln 4 times pi over 4, which is equal to pi over 4 logarithm of 2. So you are using actually a property in order to calculate in order to calculate some form of integrals. Again, if you have two functions like f and g that are integrable on AB, then you may also find another set of properties which are useful. Here, if f of x is positive, then it is logical that the integral is positive, because the area becomes, the integral becomes positive because your f is positive and you go along the x direction, so the integral must be positive. Like this one, for example, without calculating the integral to check whether it's positive or negative, that is, since this is positive, so the integral must be positive. again, if f of x is greater than g of x on AB, then it is logical also that the integral of f is greater than the integral of g. Because here, as you see, suppose f is the upper curve while j is the lower one. So the area under the upper curve is greater than the area under the lower one. So in fact, this theorem applies directly. And there is no point of checking this. If you have two functions, one is always greater than the other, then it's logical that the integral of the first is greater than the integral of the other one. For example, this one here, x minus tanh x. X is lower than tanh x. Is smaller. Is lower. Is smaller than. In other words, tanh x is greater because tanh x in fact looks like this. This is the tanh, and this is the x. So in fact, since x is smaller from the interval from -2 to -1, so you bound to get to obtain your result here that the integral is negative. Again, if f is comprised between two bounds, capital M and small m, where m and m are the supremum and infimum of f. Of course, they may be the supremum or infimum or the maximum or minimum. In fact, it's better to call them maximum or minimum for continuous function. But again, we said that they might only be integrable functions. In other words, they might be like this. For example, this is m. And the function is defined on a closed interval. For example, this is A and this is B, and this is the value f is assigned this value, whereas it has only a supremum. In other words, it has a least upper bound. It has no maximum. And yet, if f is between two values, this is f and this is j, and this is capital M. I'm sorry. You may. Here, you have here, for example, this is the value of f, and here is m, capital M, and for example, here is small m. So in fact, the area must be what below the graph of f must be smaller than capital M times b minus a, and small m times b minus a. In other words, it's comprised between two rectangles. And this is actually logical as well. Here it is. F of x here is continuous, but it may not be continuous, of course. It may have a supremum and infimum, of course, or it may be continuous and it have a maximum value and minimum value. It's the same. The area, the integral of the function f of x apparently here must be less than this area, this big area, which is m times b minus a, and greater than small m times b minus a. So it's comprised between two values. In fact, to prove this is simple by using the intermediate value theorem. Again, if modulus f is less than k, then you may have an equality like this. In fact, instead of writing this way, you can actually directly, you can clarify it in this way. Suppose you have something like this, and this is your function f. And y is equal to f of x. Of course, this area here is less than what? Is less because this is negative and this is positive and this is negative as integral. So this area is less than if you revert the sign of this part here, you get it, positive like this. So in fact, the integral of f must be less than what? That the modulus must be less the integral of the modulus f of x. Why? Because the modulus is this part of the curve here. It becomes this like this because this is when f of x is only positive. So of course this area is less than this area, and of course even this one is less than what? It's less than this area here, the big one here, the rectangle, which is what? Which represent the maximum value of f, which is supposedly is equal here to k, for example, and k could be an upper bound. It may not be the maximum. It may also be here, for example. It's immaterial. So it's less than the area of this rectangle here, and this rectangle has height k and has base b minus a. So in fact, this gives you a bound for your integral. This you can use the theorem if you have an integral which you can't calculate as definite integral. What you do is that you can bound it. You can say, for example, the value of this integral is less than a certain value, and there is no need to calculate this value precisely. If the functions f and j are integrable, then you may end up with properties like this, with some features like the mod f also is integrable, and the f to the power n, where n is m and n, and the product f j, and the square root of f for f of x is positive in an interval ab, etc. They're all integrable on ab. Suppose we have, you remember the integral the mean value theorem which we spoke about in our application of calculus. We said that if you have a function f, and this function f, for example, varies over an interval from a to b. Suppose this is time, for example. We'll take it x, and x represent time, for example. And you have a car traveling between two cities. And we said that if you, this is the difference between the distance between the two cities, f of b minus f of a. And your mean value theorem that tells you that f of b minus f of a, if you divide it by b minus a, you get what? You get the slope of this secant, and this slope of this secant must be equal the slope of the tangent at some particular value, or some value in between, called theta, between a and b, between a and b. Remember this theorem here. This theorem here is what we call the mean value theorem for differentiation. Now we have a mean value theorem for integrals, and actually the same happens here. You have it tells you what? It tells you if you have a function of this sort here, and this suppose in this time, instead of f representing distance, and you divide the difference in distance by the time, suppose f here represent velocity. And this represents time. So what if you integrate f of x dx? What you get, in fact, is the area, or the distance between the two cities. The integral of the velocity is the distance between two cities. If you divide this by b minus a, what you get is what? You get an average velocity. An average velocity, and it tells you again, this theorem tells you again, it tells you that there must exist a point in your journey in which you must reach this velocity, f of epsilon. In fact, to prove this, you may prove it using the same the same mean value theorem for in differentiation. And all you have to do is that you can, since f is continuous, then the integral from a to x or from a to b, you get from a to x first, you get another function capital F, which is differentiable, since f of small f is continuous, and this capital F of b minus a is equal, according to the mean value theorem for differentiation, is equal to b minus a times capital F prime at some epsilon, which is equal to small f of epsilon. Or you may also prove it using the intermediate value theorem. It's up to you. But the thing which is important is that the area divided by the period or the distance, the time between b and a, or b minus a, it tells you that this area divided by the base gives you an average value for your function. And in order to exemplify this, in fact, suppose this is your function f of x, and you wish, for example, to take 2 points between a and b, and these 2 points, and this is the area. If you divide this area by the base, you get a mean value for the function. This is the mean value for the function. So, in fact, if this is velocity and this is time, this height, which is the height of the blue rectangle here, it is the average velocity in which you travel along the interval AB, and there must exist a point at which you reach this velocity. And if you take another value, for example, between another 2 points here, A and B, you reach the same thing. When you calculate, of course, because you have here negative and positive values for velocity, as if you're returning back, of course, your mean velocity would be smaller, and therefore you get a mean height for your function. So in fact, this theorem is a counterpart for the differential, the mean value theorem for differentiation. And if you wish to apply this theorem, for example, on, as I said, a car traveling between two cities with the varying speeds, so the integral and v represent, you have two axes, one represents the velocity and the other is time. So the integral of v of t dt represent the distance between the two cities, while t1 minus t naught is your journey, the time which is spent in your journey. So you get here now your average velocity becomes equal to 1 over t minus 2 naught to the integral from t naught to t1. That's it. Or you may write it in this form. Actually, you may write it in the form that your distance is equal to v average times t1 minus t naught. Calculate the average heights of the 2 points situated on the circumference of the circle. Here we have a circle. this circle y is equal to square root of 1 minus x squared, and they ask you to calculate the average height. So the average height here is equal to what? You calculate the area between here minus 1 and 1, and there is no need actually to evaluate the integral. Of course, you may do so. You may, and by now you must have reached a capability or a competence in calculating such integral from minus 1 to 1, but you may also know that the half of a circle, the area of half a circle is equal to pi over 2, and therefore this is the area. If you divide this by the interval from 1 times minus 1, you get your average velocity, which is equal to pi over 4. In fact, this theorem, which is the fundamental theorem, this is called the mean value integral theorem, or the integral mean value theorem, is not the whole one, the only one. There are so many other mean value theorems. In other, for example, when you have integral from a to b of product of f of x gx dx, you may actually say that this is equal to, for example, if g of x is positive, of course, to some mean value for the integral of a b of g of x dx. Things like this, things of this sort, you may, for example, prove it by f of x times g of x is less than the greatest value of, for example, m of f, and g is positive. So since f lies between capital M and small m, and g is positive, so you multiply it by g, and then if you integrate it, you may end up with this integral here lies between capital M and small m of the integral of g of x dx, and here is again g of x dx. And since you apply the intermediate value theorem, so there must exist a point zeta at which your function reaches a value f of zeta, for example. Things of this sort. There are so many mean value theorems for integrals, like, for example, the one that we see in differentiation. With this, in fact, we came out we arrived to the end of our lesson of the properties of indefinite integral. And in this lesson, we have been displaying a lot of properties which facilitate the calculation of integrals. You may not always calculate your integral and therefore check your property. You may directly resort to your property and without calculating your integral. Again, we've seen some properties, not only even, odd, etc., but there is this important property which facilitate the evaluation of integrals, which is f of x dx from a to b is equal to the integral of f of a minus x. All you have to do is substitute x for a minus x instead of x, and you evaluate this, in fact, simplify some form of integrals. And these properties, you may find them, of course, in any book. And there are huge number of properties, and not only these properties, but these are the properties that usually we encounter, or the properties that one can think of, the most important ones. Finally, at the end of this lecture, I wish to remind you again that this lecture, along with the others, whether the one which preceded it or the ones, the very one, the only one that is going to come after, hopefully, are all uploaded to the site of the MEDNET-U, which is managed by Consortium Nettuno in Italy for distance learning. And in this link, which is provided by Nettuno Consortium, you can find all the lectures of the professors, along with the exercises corresponding to each lecture. Until we meet for our last lecture, I thank you very much for your attention, and I wish you good luck, whether in this course of Mathematics 1 or for all the other courses that you may wish to subscribe to. Again, as we shall, if God wishes, meet next time, I thank you very much for your attention, and until we meet, good luck.